Professor Keith started his academic career at the university in 1971, and he has the record for the most research dollar raised ever by any faculty member at the University of Toledo. The number last year was $75 million. It's definitely now more than 6.567. So that's a privilege to be a colleague of his and have him as part of the mechanical engineering department. That also gives me the pleasure to introduce our today's speaker, who has been a mentor and an inspiration for me for many years. Professor Theo is currently the Provost and Executive Vice President at Ohio University, probably the oldest, or truly the oldest institute of higher education in the state of Ohio. Before joining Ohio University, he served as 11 years as Dean of University of Georgia, also in Athens, Georgia. Now in Athens, Ohio, so previous in Athens, Georgia. And prior to that, he's held various administrative, research, and faculty responsibilities at Virginia Tech. His area of research is in smart materials and structure. And we are truly honored to have you here today. Please give him a warm applause.
Well, thank you very much, Dean Alahina. I appreciate the opportunity to be here. Everybody hear me in the back? Everything? Got a pretty loud voice. So, I just want to say thank you very much for coming today, and I really appreciate the invitation. I want to take a minute and thank the department chair, Dr. Sajudi, for the invitation, and just for everybody being here today. It's really an honor. It's been really a special day because, as you're going to find out in a minute, I started my academic career here at the University of Toledo a little over 25 years ago, and I'll give you a little bit short history of where I've been since then. But it's really special to come back. In short, I think you should be very proud of all that you're accomplishing here. I visited the labs today, met with your faculty, staff, leadership. I attended the Means, the Means luncheon today, which was to honor your distinguished friends and alumni. And I'm very impressed with everything that's going on, and everybody should be very proud of the great work that's going on here at the University of Toledo and the College of Engineering and the Mine Department as well. And so, again, thanks for coming, and thanks for inviting me today. I do want to take a moment and thank Dr. Keith and his wife Sandra, who I think I saw maybe came in, but I really want to thank them for their generosity in terms of creating this lecture series. It really was an honor to be invited to come. The bullets on the right are the things that your dean just said, but incredibly impressive career. And Sandra did join us, and I know that they have worked as a team throughout their career together, and so it's just great to be back. And I'm really humbled to be here speaking in this lecture series. I do have a personal note, because as I mentioned just a minute ago, I was here for a couple years as a faculty member in the late 90s. Somebody did tell me today I had a lot darker hair when I was here in the late 90s. But I do want to say that Dr. Keith, his wife Sandra, were one of the first people to come and welcome me to the university, to wish me luck, to give me some advice, and to be a mentor. So probably one of the first mentoring activities that I had here at the University of Toledo while I was here. I also want to acknowledge somebody who was honored a few minutes ago in the Means luncheon. Some of you may know Dr. Nagi Naganathan. He was the department chair when I started in 1997. He actually recruited me here to the University of Toledo, so it was great to see him being honored today for all of his work. So thank you very much, and thank you for the opportunity to be here. So I will tell you another personal story. I almost didn't. And here's the reason. When Dr. Sajudi contacted me a couple months ago and told me that I'd be part of this distinguished lecture series, I've been a dean for 11 years, I've been a provost for a few months. I really haven't done any real work for the last several years. So I was concerned, because then I wouldn't be able to come and really give you the type of technical talk that you deserve in this distinguished lecture series. But when I talked to your department chair, he said, well, why don't you, come and speak to maybe the graduate students who are thinking of a research career, maybe newer faculty, maybe reflect and maybe give them some recommendations on some of your experiences in academia. So that's what I wanted to accomplish today. I hope it hits the mark. I will have a few technical slides, but really what I hope this is going to promote is, provide some motivation. How many are graduate students in the program here? So a good number, okay? Hopefully some of you are thinking about a career in academia. Maybe we've got some newer faculty. So what I'm going to do today is really give you some reflections and maybe promote some discussions. And some people that have been around for a while, like Dr. Keith, Rebecca, or some of your senior faculty, they can tell me afterwards in the reception if I'm all wet in terms of the things that I'm talking about. So just real quickly, as your dean mentioned, I am the Executive Vice President and Provost at Ohio University, which is located in Athens, Ohio. It's about a 3.5, 4-hour drive in southeast Ohio. Being the Provost of Ohio, I have to do my propaganda slide. But as your dean mentioned, we're very proud that Ohio University has actually been the first public institution of higher education in the United States outside the original 13 colonies. Interestingly enough, I was at the University of Georgia for 11 years. They're actually the oldest public institution in the United States of higher education. They were founded in 1785. Ohio University was founded in 1804. We're very proud that the first, from what I can see, the first Black graduate of a public institution of higher education in the United States was at Ohio University. We're celebrating him this year. His name is John Newton Templeton. He started in 1824, so we're celebrating the bicentennial when he started his degree, and he completed his degree in 1828. I've learned a lot about the university in my almost 4 months in Athens. I think we have very strong programs. We have the Rusk College of Engineers, about the same size as the College of Engineering here. Very strong programs in photojournalism, communication in our Scripps College. Do a lot of work, and I think there's opportunities for collaboration in decarbonization, energy supply. About 33% of our students at the institution are in the healthcare professions. We have a osteopathic medical school as well as a nursing program and a number of other healthcare degrees. A little shy of 30,000 students. I have, as provost, I have the honor of representing over 1,100 faculty and about 900 staff who support our 250 degree programs. And we were chatting last night at dinner that Ohio University, I found out Toledo is maybe the only one that is unique in the sense that you don't have regional campuses. Many of the public institutions here at Ohio do. We have 5 regional campuses. The largest campus is in Athens, and then our regional campuses are in Chillicothe, Ironton, Belmont, Zanesville, and Lancaster. So I'm very proud to have joined such a distinguished institution. I thought what I'd do today is sort of take about 30 minutes and leave some time for Q&A and try to hit on 3 topics. I thought I'd take a few minutes and give you some technical background on my scholarship and my professional journey. Give you an understanding of sort of my research and where I've come from. Spend a little bit of time kind of drilling down into some of the trends that have occurred over my 25+ year career in doctoral education and research in higher education, and then maybe spend the last 15-ish minutes and give you some reflections and recommendations and promote some conversation. So this is my professional journey. As Dean mentioned, I don't know if you mentioned it actually, but I went to the University of Illinois Urbana-Champaign for my undergrad. I went to the University of Buffalo for my graduate degree. Went out to California, that's the star on the far left of this chart, and then came to the University of Toledo in '97, and then spent about 15 years as a faculty member at Virginia Tech. I was in their mechanical engineering department, held some leadership positions there. During my time at Virginia Tech, I spent 2 years as a program manager of the Defense Advanced Research Project Agency, DARPA, which is a DoD funding agency. And then I was Dean of the College of Engineering at the University of Georgia for the last 11 years before joining Ohio University. One interesting thing about my time at UGA is even though the university is over 230-ish years old, their College of Engineering was actually only a year old when I joined it. So I had the honor of help seeing that college grow and helping it grow over the last 11 years. And now that program is about 3,000 students right now. So I put this chart together to show you sort of where I've been. And then as an engineer, I thought, what's the centroid of this chart? I guess it would probably be maybe somewhere around Lexington, Kentucky. But spent most of my time on the East Coast, and I'm now not too far away in Alabama. And most of my research and scholarship has been in an area of smart materials and structures. Your dean is actually an expert in this area as well. We kind of work in different materials families. But I got very interested in this in graduate school and early in my career because I was always fascinated by this idea of trying to mimic the performance and function and activities of biological systems with engineered systems and devices. And the quote on the right is from a gentleman, a faculty member named Craig Rogers, who was really one of the founders of the area of smart materials and systems. He was at Virginia Tech at the time. And I think that quote sort of is, in many ways, the inspiration that I had in terms of studying that field. How do you take functions that we see in nature all the time, right, and try to incorporate those into engineered systems? And a lot of that work is focused on using different types of materials with different sorts of stimuli responsive properties. Now that quote was in 1990. I think it's always important to kind of understand where fields come from. And the picture on the left is actually, you can imagine, is a sort of an initial attempt at developing a smart material system. It's maybe a wing where you develop now we would say a kinematic mechanism to try to make that engineered system act like maybe the wing of a flying animal. That picture was actually drawn by Leonardo da Vinci 500 years before Craig Rogers' quote in 1990. And so I put this up, partly related to my recommendations towards the end is, I think it's kind of interesting and always very important to kind of know where your research and scholarship had come from. This idea of taking natural systems and trying to mimic them in engineered systems has been around for a long time, right? But it's really only the last 30 years or so that, humans have been able to do it because of advances in materials, electronics, and biomimicry. And I'll take a few minutes and talk about it. So most of the work that we've done in this field has been taking materials on the left, materials like piezo ceramic materials on the top left, shape memory alloy materials. I saw Dean in his lab earlier today. Had a great tour where they're looking at very innovative methods of manufacturing shape memory alloy materials. And then the bottom left is another smart material called terphenol D, which is a magnetically responsive material. What all of these materials have in common is that they couple different physical domains. So if you have a piezoelectric material, when you squeeze on it, it produces an electrical charge. If you put an electrical charge on it, or electric field, it will expand or contract, right? Shape memory alloys, if you stress them or if you heat them, they'll go through a material phase transformation that will make them contract. They have a pseudoelastic property, which gives them very interesting constituent properties as well. And so all the stuff that we've done in the last 30 years or so in this field is based on the fact that there's materials, some of which were discovered 150 years ago, that have these stimuli responsive properties that mimic the types of properties we see in, say, nerves and muscles in biological systems. And a lot of the early work in this field has gone from left to right in terms of taking those materials and trying to make them into devices that can be used for sensing and actuation. So the pictures on the right, look at the one on the right on the top left. That's actually a terphenol D actuator, where some of that terphenol material has been packaged and turned into an actuating device that you can buy off the shelf and use as a motor or some other type of actuator. I know your university's working on new types of stents, as I saw earlier today. That stent is a shape memory alloy material whose constitutive properties are interesting for that application. And the bottom on the right are piezoelectric actuators that you can buy and use as actuating devices. Devices like fuel injectors for cars or as sensors for ultrasonic motions. What I was very interested in my career is how do you take this and mimic biological properties? And I've always felt that that's focused in three areas. How do you take the materials that I just described, okay, connect them with feedback control systems, which really were analog control systems in the 60s or 70s, and then the electronics revolution allowed us to make feedback control systems that were electronic in nature, to make the types of bioinspiration and biomimicry that I showed you a minute ago, a few hundred years after Leonardo and Vinci thought about it. And this is my academic lineage. These are all the great graduate students, PhD students that I've worked with over my career. I've graduated about 60 students, not as many as Dr. Keith, but about 40 or so master's students, and then these PhD students. And I put this up here because it sort of highlights. So for the graduate students in the room, these are the people who did the real work, right? And I just wanted to highlight them because a number of them are still working in the field. Barbara Ackley is actually provost at Lebanese American University in New York City. Joseph Nujam, Andy Sarles are faculty members at Penn State and UT Knoxville. Vishnu just finished up a stint at DARPA. Eric Freeman's a faculty member at UGA. And, the color coding is related to sort of the three areas of work that we've done together. Initially looking at smart materials and structures, then transforming that work into look at a particular type of smart material called polymer transducers, and then look at biomolecular systems. And, just to give you a little bit of detail on those areas, this is the paper that Matt Bennett and I wrote a few years ago that looked at taking a novel type of soft actuation material and trying to make it much more stable so that it could be used in engineering applications. So all those materials I showed you a few minutes ago were all hard materials. They were ceramics, lead-based materials, right? Nickel, titanium. A lot of the work we did in the early 2000s was, along with others, is how do you make actuation-sensitive materials and actually mimic the types of properties you see in biological systems, right? Your muscles are not hard ceramics, right? Your nerves are not ceramic materials that sense. So these ionic polymer materials are materials that are soft and they're electroactive. They actually have similar physical properties as biological tissue. And what we showed in this paper is that you could make these materials last significantly longer by some interesting chemical treatment of the materials so that they wouldn't dehydrate and lose their performance. And the picture on the right is an actuation diagram for different types of materials, and the dashed ones show that these ionic liquid materials that we produced were very stable over a number of days. And so, this was an example of some of the work that we did early in our career about, trying to make new types of materials that were more closely mimic biological systems. And then a transition occurred. I did write a book in 2007. I'm not trying to copy it, but the reason why I put this up here is this book was a culmination of a number of years of work of really trying to understand the analysis and design for smart material systems and put them into a consistent framework. And this was piezoelectric materials, shape memory alloys, and other types of ionic materials. And my wife had to leave, come to town to get how we would finish this. I was actually at DARPA as program manager, and I was complaining so much I didn't have time to finish this book. She said, I would leave and take the kids away for 8 weeks. When I come back, I don't be complaining about the fact that you haven't had time on this book. And so that was the summer in 2006, and this book came out about a year later. But my work at DARPA actually was very, instrumental in that it changed the trajectory of what I wanted to do as a faculty member. Because when I came back, I was much more interested in studying even further this relationship between biological systems and engineered materials. So for several years after that, pretty much till I became halfway through my time as dean, we looked at not only making materials that mimic biologicals, but actually making materials that utilize biological molecules for actuation and sensing. So these pictures on the top right are actually small cell-like materials that are synthetic. They're essentially little bubbles that have bilayers around them. And we found, working with a number of people in this field, that you can take these materials and incorporate biological molecules in them and make them smart materials, make them change size, just like an actuator. You can make them sense their environment, just like another type of sensor. And what's very interesting about these materials is that the types of properties that they have can be tailored directly by the types of biological molecules that you choose. And so this work continued for a number of years. And what I'm proud of is, even though I'm not working as much in this area, Andy Sarles, Knoxville, has continued working and actually probably found a better application for these materials. Because what Andy and Joseph at Penn State have done is taken these materials and now they're actually trying to use them for computation rather than for actuation and sensing. So they're trying to take these materials and create basically networks that mimic biological nervous systems and to create computational systems with these biological materials. And actually, I think this is a much better application because these some of the challenges that we had in trying to use them with sensors and actuators are overcome. So, a lot of this work, all the work that your dean has done, a lot of work that we've done in this field, I think has continued in terms of making different types of automotive systems, new types of smart infrastructure, automated health monitoring. All those applications on the top right, aren't necessarily related to, our research as much as the totality of research done in the smart materials world and making actual applications that are now, everyday devices, things like wearable sensors or autonomous systems. So I think that's been a great advance. So let me pivot and take a few minutes and talk about some trends that occurred in my time as a academic and doctoral higher education, and maybe give you some thoughts as we sort of end with some reflections and recommendations. One reason why I wanted to give you a sense of my background is that, in providing some reflections and recommendations, it's really been formed by my time as an academic, my time at DARPA as a program manager, and also the work that I've done as a dean and now provost to try to mentor faculty. So some of these reflections in a few minutes that I'll give you are really based on all those different aspects of the work that I've done. But let's take a few minutes and maybe drill down and talk about, talk with folks in the room that are maybe thinking about a research career, maybe you're in graduate school, you're thinking about what you might want to do. So if you're, nowadays, whenever you have a question, what's the first thing you do? Put it into Google, right? So when you put into Google, what can you do with a PhD in engineering? This is what you get. This is what I got the last couple of days. With a PhD in engineering, you can work in academia, industry, you can have a research career, a business, create a business based on your own innovation. This is actually not that bad of a list, right? But let's take a few minutes and look a little bit more deeply at what might be some more trustable data and talk a little bit about some of the trends that occurred in the 25 or so years that I've been in higher education. So this is a chart of the number of doctorates awarded in the United States in different fields, science and engineering fields with S&E, and then non-S&E fields, and then the total. So the work that you're doing in graduate school is in the blue. Now, you can see some of the trends, right? When Dr. Keith came here in 1971, there was about 20,000 doctorates awarded by U.S. colleges and universities, and that number's a little over doubled in that time frame. You can see that PhDs in non-science and engineering fields have kind of stagnated, right, for a number of years. And so, this shows some of the trends and some of the numbers across the United States about programs like you and yours. You're studying all different institutions here in the U.S. This is a difficult chart. I apologize. But if you ask, what are the opportunities with a doctoral degree, and where do doctoral graduates typically go? This busy chart shows what's called the commitment rate for doctoral programs in a variety of different disciplines. And the way this commitment rate is defined is basically, do you have a job when you graduate this degree? Okay. Now, the number for this group is the line in red. Okay. So if you look at this line in red, you can see that it's fluctuated over the years. But generally, the percentage of students with doctorates that have a job committed when they graduate is about 70%. That's actually pretty good, right? Because that's when they graduate, right? Of course, many people get jobs 3-6 months after they graduate. But what I think this shows, and hopefully gives you some confidence studying for a doctorate, is that you've made a good choice. And there's a high level of probability that you are going to have a professional opportunity after graduation with your doctorate. And interestingly, that number has been fairly stable. There was some challenges after the Great Recession in 2008, but we have bounced back. I will say one trend, if you're a doctoral student, some of the faculty in the room that you should be aware of. This is something that I've seen anecdotally, but I think it's borne out by the evidence. When I got my first academic job in the late 1990s, it was not very common for engineering doctorates to do postdoctoral work after graduation. That was much more common for the basic sciences, chemistry, biology, physics, and the like. I think that has changed. What the data is showing us is nowadays, there's an increased likelihood that engineering doctorates would do a postdoc before they go to their next professional opportunity. And a postdoc, if you're not aware, is typically another research opportunity that's an opportunity after you graduate with your doctorate, but potentially before you enter that next stage of your career, maybe in industry or academia. And so this is a trend that I think has been happening. The numbers show that most fields have had an increased number of postdoctoral opportunities, but engineering and computer science has certainly increased in the last number of years, 20 years. And this is sort of the culmination of that, and then that maybe sort of speaks to the last part of my presentation and my reflections and recommendations. This is actually data from 2021, which actually answers the question, what do most people after they get a doctorate do after graduation? It's interesting because in engineering, you might think that the vast majority of people go into academia. The data does not bear that out. The yellow this is for different disciplines, right? In the yellow, for most engineering doctoral graduates, they go into an industry profession, right? About 11%, a little over 1 in 10 go into academia. A number less than 10% go into government, and then other types of work. And you can see how this changes with different disciplines, right? Obviously, humanities and the arts is very, very different, right? There's much greater propensity to go into an academic job, but there's a smaller number of humanities and arts doctorates. Computer science is more similar to engineering, but maybe a little higher probability that somebody would go into academia. These are the numbers in the most recent survey. The reason why I wanted to put that up there for our doctoral students and those that are thinking of the next step in their career, I think there's maybe still a bit of a myth that with an engineering doctorate, the only opportunity that you're going to have in academia. In a few minutes, I'm going to tell you, or I'm going to give you my opinion on how good of an academic job is. right? But, I think this data shows that, with an engineering doctorate, there's a wide variety of opportunities once you grad. Now, before I sort of finish up, I would actually encourage you, this data all comes from the NCESS, which is the National Center for Engineering and Science Statistics, which is run by the National Science Foundation. They do a survey every 2 years, and they publish the data. So, if you're interested, if you're close to graduation, you're thinking about next steps, or even starting your program and want to see what your opportunities are, this is a great database. There's actually much more data here in terms of where people go regionally, how this data is different by ethnicity, gender, and things like that. So this is a great data source that's maybe a little bit better than just asking Google what you can do with an engineering doctorate, but it gives you a real good understanding of what the opportunities are with an engineering doctorate. So how am I doing on time? So I want to spend maybe about 15 minutes, and when I talk to Dr. Sakuti about maybe how to pitch this talk, I thought maybe I'd spend 10 or 15 minutes to provide some reflections and recommendations. Maybe that would focus the conversation. So this is maybe for the audience in the group that's doing a doctorate, maybe somebody doing a master's and thinking they might go for a doctorate, if you're thinking of a research opportunity. But then maybe also for the faculty, not so much because they don't know this, but because I'd be interested in your thoughts on some of these ideas and how they relate to your experiences. And what I did is I thought I'd provide a few ideas, what I call the 40,000 foot level, a few ideas at the 10,000 foot level, and a few ideas on the ground. Okay? So let's start out at the 40,000 foot level. Why does somebody go into a career in academia? Okay. Me personally, and I've heard it all today, especially at the lunch for your graduates, is that, in academia, we do impactful work. We do impactful work in the classroom. We do impactful work in our research labs. We do impactful work in terms of mentoring. Dr. Keith is a great example of that, and I saw so many examples of that today on my visit. I think what's great about being a career in academia is it really gives the opportunity for lifelong learning through teaching and research. At the lunch today, I met somebody who took my dynamics class here in 1997. Gus Sineo is his name. And I told Gus that I learned more about dynamics teaching that class than I ever did taking the class at the University of Illinois. But I think if you're thinking about a career in academia, it's a great opportunity to think of how I continue lifelong learning. It's not the only job that you can do that. I think in academia, it's probably one of the few positions that allows you to do that day in and day out throughout your career. You have a lot of autonomy as an academic researcher. I would hazard to guess most academic faculty don't think they have a boss. Right? The faculty in the room don't have names, right? Nominally, I'm the boss of about 1,100 faculty at Ohio University. I doubt many of them think of me as their boss. The point is that as a faculty member, you have a lot of autonomy to study the types of things that you do, choose the people that you work with, the types of collaborations that you have. Pretty much, if you're in an academic, research and teaching environment, one of the things people tell you what to do is what classes to teach and when to teach them, right? Which is not a bad thing. So hopefully you enjoy doing that all the time as well. So what's great about these careers is the autonomy that comes with being in academia. I think it's great in academia that you can take your careers in a very different set of directions. I chose to go into academic leadership as an associate dean, and dean as a provost. You heard Dr. P, $75 million of research over what would it be 50 plus years here at the University of Toledo. What I love in academia is that you have a lot of control over the way you want to take your career and the types of job opportunities that you have. You have great colleagues, mentors, and mentees. Now, the downside is that it's not an easy job. And one of the greatest quotes I heard about academia, I put at the bottom, which is, on the bad side, you'll work 18 hours a day, but you can work any 18 hours. during the day because of your autonomy, right? So it's not an easy job, but it's something that gives you a lot of flexibility. So let me take a couple minutes and talk about some of the reflections and recommendations conversation. Starting out at the 40,000 foot level, if you're thinking about a career in academia, I really encourage you to think. One of the great things about being a professor is you can try to solve big problems. Might not always succeed, but you can try to solve them, right? You can try to manufacture new materials. So, as you're starting your career, think big, but also try to relate that work to a big societal challenge. And I will tell you, this is something I've struggled with my whole career. I like studying neat things, even if nobody else in the world cares about it. So what I've tried to do over my career, is understand how that work that I showed you earlier relates to, trying to develop new aesthetics or trying to solve real societal challenges that people are really going to care about. Because that's going to, I think, help you engage people and tell them why your work is important. You have to think deeply about your work, but I highly encourage you to practice explaining your work to a non-expert, right? And this is a trend that I've seen in 25 years. I don't know what others would say, but I started here in '97. Submitting a proposal, engaging with people. You engage with mostly the people within your technical community. Nowadays, the way money flows in research, you have to engage maybe people in completely different disciplines. You might have to engage people in marketing, business, even just to get research funded, right? And so being able to translate the big work that you're doing into something that can be explained to a non-expert in a few minutes, in my opinion, is very important. And then, focus on your core area of research, but really be willing to collaborate. I was dean at UGA for 11 years. We had great faculty there. But over time, I could see that there were some of our faculty that they wanted to stay in their little zone, right? That was okay. But, when I always felt that was an impediment, right? So what I really encouraged them to do as a dean was, think about those things that they wanted to do and they wanted to lead in their core research area, but think about ways to collaborate with others. A leader in our field, a great colleague who Eugene may know, once told me that the great thing about collaboration is 10% of the work, you usually get 50% of the money, right? And that's very true, right? If you go and write proposals, if you go with collaborative projects, often if you're not leading it, you can use your expertise, put a little bit of time in, and get the University of Georgia Gold. You can get a significant amount of resources. And I think by thinking about how to collaborate, you can really build your career. And this last bullet, and I think you have faculty. I met Dr. Lawrence earlier today. I think as a faculty member, you really nowadays, more so than you did 10, 15, or 20 years ago, have to have an entrepreneurial mindset. What does that mean? In my world, that doesn't mean you need to be out starting companies or patenting everything you do. What I mean is that you have to think every day about how you're going to get resources from the research that you want. Because, start a job in academia, they're going to give you a little bit of money to start up your work. After that, you're working to a large degree. So that entrepreneurial mindset, in my opinion, my experience, is so much about being business minded. It's being, thinking about what do I want to accomplish in my research, and how do I get different resources to give me the funds that I need to do to accomplish it. And so if we go down to the 10,000 level, I really encourage you to, as a graduate student, as a postdoc, you've been focusing on a project, you've been focusing on something maybe that your advisor wants you to focus on. But, as you think about transitioning into maybe your own academic career, understanding the types of agencies that fund different types of research is very important. We are blessed in this country to have a lot of different agencies that fund different types of research. That doesn't happen in too many places in the world. The challenge for you as an academic, the challenge for you maybe as a new professor, is to understand the difference between what the National Science Foundation is going to fund and NASA and DARPA, right? And so I encourage you to think about understanding those cultures. because the same proposal and the same idea might look very different to the NSF as it does to DARPA, right? And so, getting an understanding of, reaching out to mentors or faculty who've been successful in those areas is a great way to understand these cultures. As you get successful, keep your sponsors informed of your success. And this is something that I didn't realize early in my career. I kind of thought they were just giving me money. They didn't really care about me. They wanted to hear what I could think. They wanted to hear what I got. Because you know what? That makes them look good, right? Because if they give you money, you go out and do great things, they can say that to their leadership, right? And say, oh, this person I gave, at the University of Toledo, they won a big award, they won a national award. It makes them look better, and it's important for them and their career. Stay active in your research societies, because you never know when someone will recognize your work and want to nominate you for a national. I'm not going to say who. We had a faculty member at my previous institution that pretty much person had every attribute to be nominated to the National Academy of Engineering. That they had never been a fellow in their society. And the National Academy of Engineering will not accept you, they'll not even consider you if you haven't been recognized by your own technical society. So as students, postdocs, obviously throughout your career, making sure you continue to connect with your research labs, your technical ASME, ASC, IEEE, whatever it is, because that's, later on, it'll help you get recognized for other work or help you get into one of the national academies once you do fantastic work that warrants them. So let's maybe bring it down, and then this is where I'll finish up. If I think about ideas of just think about what you have to do on the ground. One thing that I really encouraged our faculty at UGA to do is to develop what I call that amazing chart that succinctly describes your research. We've all heard of the killer pattern, right? I didn't want to call this the killer chart, but really, I encourage you to think about, in a very succinct way, describe what you're trying to do with your research and where it fits into all the other research that has been done. Now, this chart I put up here is a chart that you may or may not use. They're called generally Ashley diagrams. This is one of my favorite charts in the world because it takes the universe of materials and puts it onto one slide, right? With with this material, or what this chart is saying is that if you look at two very important material properties, strength and density, this is the universe of materials. And this chart, when I've been at meetings, I'm not a material scientist, but a lot of material scientists are trying to talk about their new work, how to differentiate their work. They'll often use a chart like this to say how their idea is an expansion and more beneficial than the materials that have been out. Now, this is a chart that Dr. Ellen and I know very well. This is a chart that actually shows different performance of actuated materials that I showed you earlier in the talk in terms of two very important properties: the block stress, and how much stress it can produce when it's not moving, and how much strain it can produce when it's uninhibited. If you multiply those two variables, you get what's called the energy density of the material. And that energy density is actually related to the physical composition of the material. So this is a great chart because it shows that certain types of materials have certain types of performances. These are mostly mine materials. These are mostly Muhammad's materials, right? If you look at those as in terms of their frequency, it turns out that SMAs are kind of over here, and the PCTs are kind of over here. The detail learned is important, as the point I'm trying to make is that if you're doing a new actuator material, put this chart together and show where your idea could potentially be located, right? Because if your idea is down here, it's probably not going to be fun. If you're sending a proposal to the National Science Foundation or DARPA, you show them that your idea has the opportunity or the potential to be better than any other material around, it gets their attention and it could potentially help get you funded. Okay. Over my career, I've really thought of the idea of what I call cycle management. We all know about time management. I think time management is a very important skill, but over the years, I've kind of turned this into a topic I call cycle management, which is the relationship between the amount of intellectual cycles you expend and the quality of the work that you're doing. But let me give you the event in my career that made me think about this chart. I was preparing for my advanced control class doctor at Virginia Tech. And it was early in the days of PowerPoint. And I remember that I did my lectures on PowerPoint. And I was trying to put my chart together. And it was just a block diagram. And I was trying to line up the things, that they looked really good. And it took me, this is before all of the auto connected, things like that. And I finally stepped back and I thought, it's taken me 10 minutes to do this. And nobody in my class is going to get it. Right? So that's an example, a small example, where, over the time of your career, I think you start understanding how much time you like to spend on something to get a particular level of quality. Right? How much time do I have to spend to make that proposal as good as it could be? And this is something that I think is a skill over time. Hopefully you're learning as a graduate student or postdoctoral student. And this type of, understanding of yourself, I think will will serve you well as you go into your career, whether that's in academia or somewhere else. The last couple of notes, if you're thinking about going into academia, recognize that over time, you're honestly not going to do much research. You're going to become more of a researcher, right? If you're going to be the one writing proposals, you're going to be the one advising the graduate students, you're going to be the one going out and collaborating and building networks, So yes, you're going to be doing the research in the sense that you're directing it. But you're not going to be the person generally in the lab. You're not going to be the person who's going to be doing the day-to-day work. And if I see where the faculty that I've known over my career, where this has been a challenge for them, it hasn't been a good situation because they don't necessarily grow to their full potential. And then finally, I really hope that if you go into career in academic research, that you embrace your role as a mentor and ensure that you're presenting or promoting your mentee's success. At lunch, I heard about a lot of people who took Dr. Hesse's class, Dr. Pete's class, Dr. Kramer, right? And the impact that those people have on the trajectory of the individuals who are being on. Okay, and sometimes I don't see faculty as focus on this as much. I think it's an opportunity for us as faculty to be good mentors and we embrace that part of our job because again, not many jobs that's not an element of work that we do. So embracing it is very important to your success and your mentee's success. And I'll give you a bonus one, which is, if you're thinking about this stepping, it's one of the best jobs that you can have, I think. And while it's challenging, it's a great job for all the reasons I said earlier. And just having fun and enjoying the ride is probably one of the best aspects of being in a research career and being one. Thanks very much.
Thanks for questions. Yes, good talking. Thank you so much.
Zero equations.
This is important. Don't take them. Yeah. If you go back 25 years, what would you have done differently in terms of your research?
I think I would have done a better job. I mentioned about thinking about how your work impacts society in a big way. I don't think I did a very good job of it. I think in retrospect, I think I was doing good work and solving important problems. But I think that, in hindsight, I probably would have tried to figure out, how does the work that I'm doing with sensor materials, actuator materials, really try to address some significant societal change. Because I think later on in my career, I realized that it does, and it did. But I don't think I articulated that very well. I always felt very jealous of people who were in biomedical fields because they could say, well, this number of people, have cardiac arrest or, cardiovascular disease is the biggest, killer in the United States, and here's what I'm doing to try to address it. I think I really struggled with that early. Yeah, I think that probably did it.
Let's ask a question. Probably on behalf of the audience, we have a lot of grad students here, and you mentioned 75%. That's a great news. So for them to find a job after graduation, doubling down the numbers. So the graduate life is difficult for students. You're basically doing research for a lot less money and a lot of issues. But yet today at lunch we saw a lot of success from many years ago that the students connected and networked. And so what would be your recommendation for our body of students in terms of interactions, building the network? You mentioned the building the network within the societies, but we saw at lunch today that some of those people that were here like 25 or 30 years ago now are very successful. So what are your suggestions to keep motivating our students to interact, build a network, have collegial and friendly interactions with each other, knowing that we will soon meet somewhere again in the future?
No, that's a great point, and I think you're exactly right. I mean, my recommendation is to do, in many ways, what you said. And I think in my experience, I'd say my professional network that's had the most impact has been heavily weighted towards the connections that I made in graduate school. And not all of those people went to onto an academic career. A great example is one of the students that I worked with at the University of Buffalo State Recognition. He's an Air Force program manager now. He just visited Ohio University about a week and a half ago. Right? I'd say, the professional connections you make with a graduate student are often the ones that continue throughout your professional career. Because oftentimes, those individuals will work, even if they work in a different field, they're working in a related. Right? Many times, those people become leaders in their organizations, even if they go into a very different organization. So I think that's part of it, which is, how does that sort of connection impact your career? But I will tell you, I think, you also asked a question about the community that you have. I worked in a research group that was probably on average 20 to 30 students at any one time. I had a fantastic advisor. That was my advisor very well. But I could count on one hand the number of technical conversations I had with him. Just because he was the type of person that he wanted you to come up with the ideas. He wanted you to sort of self-direct your work. And I bring that up not as a negative. I bring that up as a positive because I think it helped me when I became an academic. But to your question, really you learn from the other graduate students. Right? Somebody else was doing an experiment that was similar to mine. Right? If I had a problem, I didn't go to my advisor. I went to my colleague and my peer because I knew they were going to help me a lot more than my advisor. So I think there's two answers to your question. One is building that community while you're here so that you learn from one another, right? And then building that community while you're here so that when you go out and have your professional career, those are people that you can continue to interact with and help one another be successful.
Yes.
Yes. Yeah, I have, sir.
Sure.
So you've taken a position at a university, and of course you'd like to succeed, you'd like to be promoted, assistant professor to associates, and you recognize you're going to have to do research, or well, let's say you're going to have to teach. Could be teaching at the undergraduate level, the graduate level, both. You're going to have to do research, which means that you're going to have to go for funding. You have to publish papers, and you have to work with graduate students. You also have to worry about service, working on committees, working in societies, and that. And so, as an administrator, department, dean, whatever. Faculty member like that comes in and says, okay, I have to do all those things, I'm being promoted. What's the most important?
Well, it's actually you say that because a number of faculty at the time that I interviewed with the PTA was asking that question. They would ask me a different variation of that question, which is, what do you expect me to be the best at? And my answer would always be, I expect to be excellent at everything. Just a little bit of courage. I think that part of the answer is that you do have to excel in all those different aspects of your job. But that's not as hard as it sounds, in my opinion, because, it kind of gets back to that comment about cycle management, right? I think, the scenario you painted is hard for a faculty member because, in my mind, the different time scales associated with all of those activities, right? You have to be up in front of 75 undergraduates the next day, or makes your lecture is good, right? And maybe that proposal to student a few days is going to have to be close. So I think a lot of it comes down to, how do you, have the level of quality in the different aspects of your job, but manage it appropriately. So that, that you're achieving all those goals simultaneously. And I think people can do that. Where I've seen people not do well is they really don't manage their time or manage their effort in a way that allows them to, have success in all those different aspects. But unfortunately, I'm not going to name the person, but that faculty that I mentioned, that probably could be in the NAE if they had, they made a decision early in the career that they were too busy to go to their professional society meetings, right? And, they were too busy teaching. That's an unfortunate example where I think that, if that person would have been mentored early in the career, say, no, you really need to take that 1 or 2 times a year and be active in your research or your technical. They wouldn't have had that impediment many years later. And so I think it's, part of the answer is having the right mentors around so that they understand how you can balance it and really excel in all those different aspects.
But it does reveal that it's autonomy or freedom there, you have this better. It's really like a double-edged sword.
You're right.
Because you have to decide. And I used to tell faculty members that have something like that. I'd say the single most important thing is whatever you don't have.
Right.
Because you're going to be evaluated by other people that are in your profession, that are doing the same type of thing, and they will look for weaknesses.
Yeah, I think, that little quip about, you work 18 hours a day to an 8 and that's pretty good. I mean, I think the challenge in academia is to you have to be good at all those different, I mean, it's the challenge and the fun of it, in the sense that you really, you have to be good at the class, and you have to be good at the research, you have to be good school in your profession. I think where I've seen, I don't know about others who see it in the leadership positions, but I think the people that I've seen that have struggled with that, it's not that they're not talented enough, it's just they're not understanding the various balance of aspects of it. That's what I've seen as being one of the impediments.
Yeah. Thank you for the opportunity. I really like the ideas, recommendations you made, especially the amazing chart, the killer chart. I'm trying to say that I benefit from the idea of inspired ideas for research and did my doctoral project on interplanetary communication. But if we think about the 500 years of research journey from Platon to here, from Da Vinci's idea to the idea we explored, if we may use, say, a mind of knowledge that would come from nature, and do you think the mind has been already mined enough that we have to dig deeper and wider to find some ideas on the nature to explore new ideas for research? or you feel there's some systematic way people can use or methodology they can use to learn from the nature and apply in their research?
Yeah, I mean, I definitely think there's a systematic methodologies. I think part of your early part of your question is, I think you asked, can you know what enough about the mind, to understand. I don't think we do, all of the caveat that I'm not a cognitive expert. I mean, I think in the field that I've been most closely related to, I think that the challenge that we have yet to overcome is the materials that we use to try to mimic biological systems are fundamentally different than the ones that biological systems do. And so I think the challenge that we have is that while we can often approach the functionality of those biological systems, you approach it in a way that is very different in nature. And so, in the end, we fall short because we're limited in the materials that we can use to try to accomplish those functions. And I think one reason I put that work up from 80 Sorrows is that, I think that, the idea of using these biologically inspired tools for computation, right, is kind of addresses, I think is a step towards trying to address the question in the sense that, yes, we can mimic, say, the brain's function in a silicon system, right, on a computer, but, asking the question, the downside of that, for example, is that it uses tremendously more power, right? So, you ask the question of how do we mimic those biological functions, say, at the human brain with less power, and then, it draws you to try to see how you can use biological materials to try to accomplish that task. And I think that's an example where there's still a gap. So I do think there's systematic methods. I think that I think the challenge that we have in this field is that the materials are still not caught up to our ability to mimic biological systems and to really mimic their functionality in a way that has the elegant solutions that nature has designed over millions of years of evolution.
You haven't got the full understanding.
Oh, we haven't
Brain,
got the full understanding.
Yeah.
Yeah.
Okay.
Thanks.
One last question.
One last question.
Sure.
If you feel it's the personal, we're not going to answer. I understand from these papers that you showed, also your experience with DARPA, and so you are and you were very successful in research and science. But you decided to go to our administration works. Would you mind telling us why or would you recommend?
Oh, sure, yeah. I think it's too personal, but I've thought about this a lot. I've even got it a few times. And, I think where I come down on this is, I think as faculty members, we all want to have. And, the impact that Dr. Keith has had in terms of research and mentoring and teaching, the impact that you're all having as faculty members. I think there was a time after I came back from DARPA where I thought, maybe the impact I want to have is by helping develop programs and helping programs. And, that's what sort of, if for the faculty in the room, if you're thinking about these things, it was really good for me to take an associate's dean job, for a few years. I worked for a very good dean, Dick Benson, he's just stepping down as president of UT Dallas. And so that was a great opportunity for me to see how he operated and the type of job he had, right, and try to decide whether that's something I wanted. And then, the same thing as a dean, I've seen how our provost operated, made me think I would be interested in trying to have that sort of opportunities with them. So, I think in the end, it all comes down to the type of impact that we want to have. Over time, that's growing into the types of positions I've had for the last 10 years. So, thank you.
Great, let's thank.
Thanks, Steve.
The extension outside.